Hi, so today we're going to be doing an introduction to Verilog. We are going to be taking a look at basically a transition from the analysis of how processors work, so for instance, how an Atmega 328 works, to the synthesis of behaviors for processors, so the development of basically the hardware that makes that happen, on systems like a field programmable gate array. So that's a different type of chip. Now, in the course, we're not actually using the hardware, but this is eventually where these thoughts sort of direct you to. So we've been scratching the surface as to how the behavior and interaction of components for microprocessors and microcontrollers work. But now that we've got an idea for how these microprocessors behave like actual real ones, we can delve more deeply into those internal interactions. So we want to we want to learn about how we model individual subcomponents to validate their functioning, to combine them together into subsystems, and then to validate those combined subsystems. We're going towards the point where we could develop meaningful subsystems like arithmetic logic units. So I want to go over how we bring those details together to make something meaningful that could eventually be deployed into one of these basically blank chips, so that the chip itself would do what you created in your hardware description language model. Okay, so we went from analysis, and now we're going to synthesis. All right. We use programming languages like Verilog or VHDL, or, well, there are a number of different languages out there. And these languages look in a lot of ways like programming that you would do in a language like Java or C or even MATLAB. The syntax and the structure of Verilog is similar to these other languages, but because what we're really trying to do is not create an app, but specify how the interconnections inside of this chip work, the syntax and the structures will diverge a little bit, a lot really, from what Java and C really look like. But there's some similarities. Now, basically, you will be writing in a text editor a program, okay? And that program has names, and it has different structures, like this business right here, that where something begins and ends. It has an end point, and it has, say, a name up here. And then you have variables like the definitions for these registers that you see up here. Once you've created this, then you move over to an environment where you can actually compile and execute that text. And so in this case, what we're showing is that you can use a shell or a terminal, okay, by going to, say, a place like remotelab.eecs.yorku.ca, and you can compile using iVerilog your text file, and then you can run it afterwards. That's effectively what we're going to be doing. Now, Verilog is used to model circuits, and yes, it is a little bit, or depending on your perspective, a lot like programming in C, MATLAB, or Java. Those programs that you're writing are effectively tasked with creating structures and connections and implementing algorithms in a language called Verilog. So you're effectively forming a model, okay, that has the behavior and structure of a circuit, okay, like a digital circuit. Now, this is more modeling than it is the typical programming that you do on a computer. And in some ways, it's similar. The difference between an implementation and a model is the difference between an actual house and the plans that are created to allow that house to be constructed, okay? That's the difference between modeling and actual implementation. So here we're really doing the modeling before we actually end up putting it on the chip. So we're going to be focusing on writing those programs to show those behaviors that we want. All right, so Verilog, this language that we're going to be showing you, is an entry into the world of field programmable gate arrays. Now, there are different customizable chips out there. And what do we mean by a customizable chip? Well, inside of these FPGAs, there are basically a whole whack of transistor blocks, and they are laid out in a very regular form where they can be said to talk to one other transistor block or another transistor block, but when the power is up, it doesn't know which ones it's supposed to talk to. So you've got these individual little blocks like this, and they're isolated from each other. And your job is to say, I want this block to talk to that block, and I want this block to connect to that pin on the outside and maybe that pin on the outside. And then I want this one not to connect to any pin at all. And this one over here to connect over here. That could be maybe connected up to a monitor or a USB port or something like that. And then you deliver it to your customer. But then your customer comes back to you and says, well, you know what? It didn't work out quite the way I wanted. I wanted this USB 3 connector to be in here instead of a USB 2 connector, and it's got to have this other little device connected up. So instead, we're going to have that pin connected up and that pin connected up as well. Your new program goes into the chip to make that happen. That's effectively what the FPGAs are capable of doing. At small and medium scale, that works really well. If you need to have a customizable chip that is deployed into really large-scale applications, then often you're talking about ASICs, or application-specific integrated circuits, which are more cost-effective than FPGAs and don't have the flexibility of FPGAs after deployment. But in both cases, what you're doing is you're saying the chips that are on the market, like this right here, aren't doing what I want them to do. I need to create my own custom device. That's effectively what we're talking about here. All right, so what do these Verilog models, these Verilog programs look like? Well, they start with a name for their module. Then you define registers, okay? And you specify the size of registers. So right here, this is a 1-bit register, okay? This over here is a 3-bit register where I specify it's got bits 2, 1, and 0, okay? I then say that I want to basically initialize something, and then I want a block of behaviors to start, and I want them to end. And then I specify that my module has an end. Inside of my module, I can specify that things be displayed to the terminal. I can specify that a register change value. And then I can also specify equations that describe the changes in those registers, and then display as well. I can then combine registers together, and then I can make more displays, and I can program in logic connections. That's basically what's going on in these kind of files, okay? Now, once you have got your model going that you've written up in a text editor, okay? So you've written it up, then you have to run it. How do you run it? Well, basically you go to a place like Remote Lab or EDA Playground or something like that, and you take your text that you've written and you compile it. So in this case, what we do is we do iVerilog and then the name of my file, which ends with an extension .v, and I hit enter after typing that into the terminal. Then I say that I want to execute the file that resulted from this. Okay, so when I compile, it creates a file called a.out, unless you specify a different file name. Then I say I want to execute it. In this case, I'll use VVP to execute it. So I say execute the compiled file called a.out, and then it will display my display commands at particular values of time, okay? And then it might specify that things have changed inside of my circuit. And then my job is to take a look at this line and that line and that line and that line and what was displayed to see if it gives me the behavior for the circuit that I wanted. So that requires you to have some thinking that goes into what you display, and what sort of testing you do. All right, so when you start doing that, it's important to point out that it's okay at the beginning for variables to have undefined values, or we sometimes call it don't care. So we don't care what the value is, or the value is undefined. So if a variable is displayed as an X, it means that it's in a state of I don't care what its actual value is. And you'll see that often in Verilog models. You'll actually see it a lot in descriptions about digital circuits, where things might get initialized or might propagate through, and at some stage, instead of a 1 or a 0, that thing, that variable, that register has a I don't care value, an X. So it could take a value of logic 1, logic 0, or other values too, if you want. All right. Something else that's important to point out is that you often need to insert delays into different parts of your circuit. So you can specify when some aspect of your model is going to get executed. Does it get executed at the beginning? Does it get executed 10 time steps in? Does it get executed 100 time steps in? This is something you can actually specify. So you can make things run sequentially. That is, one thing after another, after another, after another. Or you can also specify it so that two things are running in parallel to each other. Okay, so sequential and parallel are both possible. You can use delays, or you can introduce delays, and you do that by introducing them at the beginning of a line. So in this case, if I had y is equal to x plus 1, if I wanted to introduce a delay that meant that y is equal to x plus 1 happened 10 steps further along, then I would put a number sign or a hash symbol and then 10, and that will make it execute with a delay of 10. Now, what was that 10? You can specify what those units of time are, but generally speaking, at the stage that we're at right now, it actually doesn't matter if it's picoseconds or nanoseconds or milliseconds. It's just 10 units of time. Now, more about delays. You want to set up delays for different stages of the circuit so that signals arrive at particular levels or layers of the circuit as needed. So effectively what you're doing is you're specifying that it propagates through a circuit. So basically what you're saying is that if you have say A and B, and then you've got C like this, and then you've got, say, an inversion right there, and then you need to combine these together. Okay. As signals go from this end to that end to that end and then out, it takes time to travel through this gate right here, and it takes time to travel through that gate right there. That time that it takes to get through those individual gates is non-negligible. It actually takes time for the circuit to change inside of here from the inputs to the outputs. And so as signals propagate through, you can't actually have a signal change, and you don't want a signal to change immediately here and have its value immediately change there. It's not going to happen in the real world. So it takes time to travel through that, it takes time to travel through that, it takes time to travel through that. And so you may have to specify that signals that might come in from different points in the circuit take time to get through this, take less time to get through that. That's what the delays in propagation that we're talking about are really about. So so basically you want to plan that out, how it goes through your circuit, so that you don't display, for instance, the output too early, because the signal that started over at this end might in real life not have had a chance to make it all the way out here. Okay, so you have to keep that in mind as you're creating your model. And in the lab descriptions that we've got, the lab activities, we talk about where to insert those delays. Okay. Now, you can also run things in parallel, and each parallel block starts with the initial keyword. So that's something else to know, that you can run these things in parallel. And one example that we talk about in the lab is having this monitor line that's an equivalent to the display commands, and these will be running in parallel to the block of other commands that you've got that are actually in charge of making the circuit change. Okay, so this is something that runs in parallel so that you can have constant, reliable updates to what's going on inside the circuit. All right, so for instance, you've got your task 1, which is the monitoring block, and then you've got task 2, which is really the system that you're testing. Okay. Now, when you're simulating circuits, you can simulate logic objects like AND and OR gates that have both inputs and outputs. You have to define both those gates and the wire names. So you've got, these wires right here that connect in and connect between different gates. So here's an inversion, and there's an AND. There's a wire in between. And in order for Verilog to know what you're connecting up together, you have to specify that the output of this is going to be the input, at least one of the inputs of that. So you do that by naming that wire in between. So you need to define wire names that connect these inputs to the outputs. And effectively, you are creating a net of interconnections. Okay, so in the first Verilog lab that we've set up, there's a part 1, which is basically how to get started, how to add delays to models, how to create simple circuits, testing the model, doing things a little bit more complicated in terms of testing, doing more complex circuits. User input during testing is introduced. Then we take a look at a slightly complicated example, a multiplexer, and then an even more complicated and useful circuit called a full adder. So that's what happens in the first lab. So you have to go through all these different steps. When setting up your model, it's, I think, really, really important to draw it out on paper. So basically, take a piece of paper and write it, okay? Label everything on paper, because in practice, most students get confused as they type things in as to what was intended in the first place. So in order to derive meaning and to be able to debug things properly, draw out the logic gates. Draw out this AND right here. Draw out the inversion, okay? Show where the inputs are. Label what these individual inputs, and then write in what the wires are going to be called as well. Okay, like this is really important. So do it on paper, draw it on paper, label everything, and then once you're done, program it up. Or if you don't believe me, program it up first, then get confused, and then go and redraw it, sort of go back the other way around. All right. When you are writing up your program, I think it's really important to write up different versions of your Verilog program. Rename it as you're as you're developing it. You can copy from the command line, or you can use your text editor and create different backup copies. I think it's a really good idea. It's good for safekeeping, and as you're creating your system, take a look at what your errors are, because you'll have errors, that happens. And if you don't, or if you're not able to debug the error itself, then sometimes a really good idea is to start from scratch again. Okay, so just erase the file, or save that file, start a new one, and try again. And this is one of the typical ways of getting through potential errors that you encounter. Okay. In our approach to testing or creating models, we set up tests. And in the lab documentation, these are being referred to as oracles. They allow you to create your circuit basically you create your circuit using nets and ports. Then you test them against basically gold standard logic statements. Then you run your test using loops, and then the idea is to watch the output. Basically what you're looking at is the combination of inputs and to see what happens on the output. And if a value of A is equal to 0, a B is equal to 0, and C is equal to 1 is supposed to give you an output of Z is equal to 0, then you say it passed. If, on the other hand, you put in A is equal to 1, so this is an input, B is equal to 0, C is equal to 1 as an input, and your output is 1, then you say, nope, it failed. And this is a way for you to examine if you programmed up your Verilog process properly. Okay, so that is the intro to Verilog. Really at this stage, it's just going to be important that you try it out, that you go to the lab, you can ask questions of the TAs, and you do the demonstrations as instructed in the lab documentation. Good luck, everyone.